Great. Today was the drop dead deadline for me to determine whether I was okay giving an exam a week from today. My conclusion, I'm not. So I'm making the executive decision based on the amount of material that we've covered and just the interactions that I've had with people to push that up a week. Are there any questions or concerns about taking an exam from Friday of week 3 and moving it to Friday of week 4? What this probably means for the class is we will not have 4 exams in here. We will have 3 exams, something like weeks 4, 7, or 8, and finals. So make the associated adjustments in the syllabus or in any mental note of what we are doing. If we had an exam next week, I would have to, you're going to have this one assignment, the only assignment that you would have had feedback for, and the grader would have 46 assignments and a day and a half, just about a day to turn that around for you to get any feedback on how good that assignment was before you took an exam on that material. And I would have to write an exam solely on that one section. And I don't think that's going to do anyone any good. So that's my reasoning behind that. Anything else before we dive in? So I do give people a study guide a week before the exam. So the new plan is study guide a week from today, exam 2 weeks from today. Yeah.
Will you have like any practice exams available, or is it just going to be like study guide?
This is the first time that I've taught the class. I probably am going to need all of the problems and preparation I have to think of and come up with questions for the exam. The study guides that I do make are usually relatively, it's not just a list of topics. I try to word them as questions when I can, things for you to ask, do I understand this or not? I am also okay publishing some extra sections of the book problems. So I've taken snapshots of just the problems that I've assigned, but I can snip some of the extra problems from that as well, and those can be used as practice problems, not necessarily a mock exam, but more of a, now that you've had the iteration of doing this assignment, getting feedback on this assignment, when I try a similar kind of problem again, how does it go? Yeah.
I know you haven't written the exam yet, but do you foresee the exam having questions that are more wordy or explaining what's going on, or more like mathematical, where you're going through finding anything?
Some of both. So I plan to have some questions that are styled similarly to the homework problems, and some problems that are querying more at your higher level understanding. Not just can you solve this one particular kind of problem, but how do you see the interrelation between these concepts, or between, to have you explain how you understand it in your own words, rather than trying to match your explanation to a problem. I try to balance that out when I can. Very little regurgitation, either problem solving or higher level understanding of concepts that are going to, they're not going to be words that are directly on a study guide that you would make, but require some interpretation and understanding of. That said, when I do write the exam, I go back to the study guide and I get inspired by something on the study guide. So there isn't going to be a question that's completely out of left field, not on the study guide whatsoever, but it might be related to or similar to something on the study guide that's not specifically on the study guide. Be able to do this. The question that is asked doesn't tell you to do that. You need to know to do that in order to answer the question. So knowing how and when to apply things because of the wording of the question. That kind of thing. In general, I do have the expectation of a general higher level understanding of the material. And I try to avoid any questions that are multiple choice or true or false because I don't like them. They are. This is why my graders think that I hate them. And or I think that I hate myself. All right, let's dive back into material. Any other questions before we do that, just to make sure that I have everything answered? All right. Anyone get a chance to think about this intro version of the hiring problem from last class? I figure you all probably had some other important things to do, but yeah. Got a chance to think about it? Yeah. So we're going to go through some of the steps and ideas that you might want to apply to this problem as we work on this problem. So the first thing we're going to need to do, I think we went over this slide.
I think we did.
Yeah. We are here. We're going to look at the concept of indicator random variables. So we have an event, like the event of hiring somebody. We're going to define an indicator random variable as it's binary, it's true or false. It's 1 if the event occurs, 0 if the event does not occur. An example of this, let's say flipping a fair coin, comes up all the time in probabilistic analysis. So if the sample space is just heads and tails, we know that it's a fair coin. This makes sense. Probabilities of heads and tails are the same. So we could use an indicator random variable for an event like a flip coming up heads. So now we've defined the random variable x sub h, meaning the random variable that is heads, as now we're saying is we have an indicator random variable representing that heads. And that is 1 if heads occurs and 0 if heads does not occur, which is the same thing as saying if tails occurs. We can now apply this indicator random variable to a sequence of events. So single events as well as sequences of events. We can start to take the expectation, the expected number of heads on a single flip. It's 1 times the probability of heads plus 0 times the probability of tails. 1 times 1/2 plus 0 times 1/2 gives us 1/2. The question though is extending this onwards to n flips. What changes do we make to this logic in order to get there? What's the difference between n flips and 1 flip? Yeah.
Replace the 1.
Replace the 1 with an n. Basically, we're going to sum every individual event since they are independent. The value of the first flip does not affect the value of the second flip, does not affect the value of the third flip. So we could treat them all as you're breaking down a sequence of flips into a bunch of individual single flips. And then we just take the expected value is the sum of the value of that indicator random variable on the ith iteration. Breaking that down, we just see the sum from I is 1 to n of the expected value of the indicator random variable. Since the expected value is 1/2, we just sum 1/2 plus 1/2 plus 1/2 plus 1/2 n times 1/2, which is n over 2. And intuitively, we can map this to the idea that you flip a coin 10 times. The expectation, not guaranteed, but the average case of this is you would have 5 heads. So this maps to, again, to our intuition of this. So this is just an introduction to the concept of an indicator random variable. Anytime you have a binary problem, either an event occurs or doesn't occur. So let's try to apply this back to the hiring problem. So our random variable now will be the number of hires, and we can break this down into the event we hire or we don't hire. So the expected value of this indicator random variable is the sum for all of the candidates that we see from the first candidate to the nth candidate of what we're going to say the probability that we hire that candidate. So as an indicator random variable, we say each of the candidates is the ith candidate when we interview them, and the indicator random variable will be true if we hire, will be 1 if we hire that candidate, 0 if we do not hire that candidate. So we could then say the number of candidates that we hire is just the sum of the expected values of each of those indicator random variables. The probability that we hire the first candidate, plus the probability that we hire the second candidate, plus the probability that we hire the third candidate, all the way to the nth candidate. Any questions on anything so far? Turning this into a general argument, trying to condense this down into something that makes sense. How do we come up with the chance that the ith candidate is the best one so far? That is what we need in order to hire that candidate. It has to be the maximum of every candidate that we have seen so far. We know that's going to be true on the first candidate because there's no benchmark. The second candidate is either higher or lower than the first candidate, and the first candidate on average should be an average candidate. We would expect the value of that to be about 1/2. What's the probability that we hire the third candidate? What is the probability that in any distribution of 3, that the third candidate is the highest value? 1/3. So yeah, every candidate from 1 to I is equally likely to be the best of the first I candidates. So the probability that the last candidate, the I query candidate, is the best candidate seen so far should be 1/I. That maps fairly intuitively. How are we doing with that?
It makes sense now.
So we can take this idea and now turn this into our sum. And if you're curious where this is in the book, when it says by equation, et cetera, it's applying equations that it's talked about, but I can explain any of these. So the expected value of the full random variable, remember that is just this x, the number of candidates that get hired. So the expected value of the number of candidates that get hired is the expected value of the sum of the probability that we hire each candidate. That makes sense. Just doing this first line right there. Expected value of the number of candidates that we hire x is the expected value of breaking this down into each individual candidate from 1 to n, and the probability that we hire that candidate is represented as x sub I. So x sub 1 is the probability we hire the first candidate, x sub 2 probability we hire the second candidate, and we just do that for every I from 1 to n, since we are hiring or interviewing n candidates. Breaking it down further, rather than taking the expected value of everything, we can note that because of the linearity of expectation, or we can move the expected value inwards to say it's the sum of the expected values of each of the individual candidates. Does it make sense as to why that is? The expected number of candidates that we hire is the sum of the individual expected chance that we hire each candidate. Rather than taking an expected value over everything, we can sum the expected values of each of the indicator random variables. The expected value of this is the sum of the expected values of these. That's what we're doing by moving this expected value inwards. The expected value of the whole sum is the expected value of how many candidates we hire. Moving it inward is saying now it's the sum of the expected values of each individual component. So we can look at them independently and ask the expected value question independently, rather than trying to take the sum and then find the expected value of the sum. Okay. So next step is to say, all right, well, what is the expected value of each one of these individually? We said that was 1/I. So this becomes the sum of I equals 1 to n of 1/I. We're looking at 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, etc. How does that grow asymptotically? We just conclude here that it's the natural log of n plus a constant. But it is what we call the harmonic series. One fun fact about the harmonic series is it diverges. For those who don't know what that means, it doesn't approach a particular value. The sum of this series continues forever. There are some number of terms for which the sum is greater than 10. There are some number of terms for which the sum is greater than 100. Anyone have any intuition as to why that is? I love the harmonic series for this reason. One of the stranger results. It seems like if the number is going to get smaller and smaller and smaller, that we should be approaching some value. And a similar series that does approach something is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/2 to the k.
Yeah.
What is that approach? What is the limit as we have an infinite number of terms of that series?
Feels. Familiar.
Good. Any guess? What does this converge to? Yeah. E is a good guess.
Well,
It's wrong, but it's a good guess.
I feel like it has to.
Yeah.
No,
So we have a 1 term here. So this 1 can basically be factored out. The question is, what is 1/2, 1/4, 1/8, etc. approach?
would it eventually equal 1 or? am I
It does. The limit there is 1. If my goal is to move myself from here to the wall, the first term says move half the distance. 1/4 says move half the remaining distance. 1/8 says move half the remaining distance, and every single term will get you half the way from where you are to your goal. So you will get arbitrarily closer to your goal, but never get there. But there is no place before the goal that you could give me that some number of these terms wouldn't eventually reach. I could say 1 millimeter before the wall, and there would be a certain number of terms where I would get to that point. You could say 1 yoctometer, and I would eventually get there, but I would never reach the wall. Yeah.
First 2 terms, but you got 1.5, how can you get below
It's the rest of this is 1.
the rest of it?
Yeah, so this whole sum is 2.
What does that now?
But the harmonic series that is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, this diverges. The sum of this series, if you incorporate an infinite number of terms, is infinity. Why is this different from this? This approaches a real value, in fact, a relatively small real value, but this goes on to infinity. There's something different here, yeah. You're not dividing by half each time, but it is a smaller and smaller and smaller number. Anyone have any intuition as to why that diverges?
Well, then. I think I see it. Well, the previous one that we did up there basically is going like just half the distance every time and not. I'm going more than half the distance every time, so in this case, we're talking about it increase like. Fraction increasing by 1 every time, and
Yeah.
it's gonna continue on indefinitely. Because. There's so many numbers that people lose track, like. I'm thinking, I have the right idea, but not the right reasoning.
Yeah,
The one, you know, that's decreasing that, that's the second one.
Oh, yeah, it's decreasing at a linear rate?
it's not like
No, it's not. That's right,
It's not exponentially.
No, it is.
the denominator is increasing at a linear,
Yeah, it is, but
but the value is not linear.
it's.
Yeah,
Quadratic.
Even though the fraction's getting smaller and smaller, you're still making progress over time. You're never that amount of progress.
Yeah, if we look at these three terms, here we have a value that is one. Looking at these three terms, are these three terms greater than or less than one?
Less than. Wait, no, greater than one.
It's greater than one. We have 1/2, and something that is greater than 1/4, and something that is 1/4. That sums to something that is greater than one. If we looked at the next 6 terms, twice as many terms as this, they would also sum to something that is greater than one.
Yeah.
If we looked at the next 12 terms after that, they would also sum to something that is greater than one. So we always have the ability, using twice as many numbers as we did last time, to add one to our amount.
Okay.
So there is no number for which this can reach with enough terms of this expansion.
I see it now. So this is, you said this is harmonic series?
It's called the harmonic series. It's worth the interesting study because it's a little bit non-intuitive.
At least I understand, I think.
That was a total aside, but I just like to think about math when something like this comes up and you get fun, interesting results from that. It's interesting to look at why or what interesting properties does this progression have, and math is full of those interesting tidbits where you analyze it and you start to understand more about math just by looking at how something changes. All right, so the sum of the harmonic series, not something I'm exactly going to go into, but if we're looking at the sum of 1/i from 1 to n, that is going to increase at a rate that is proportional to the natural log. And this makes sense that the harmonic series diverges because the natural log also diverges. You need more and more and more terms for the natural log to reach the next integer, but there is no cap to the natural log. The natural log of some very large number will be whatever arbitrary number you would choose to be. I don't want to phrase this. If you gave me a number, any number, I could tell you the number of n such that the natural log of n was your query. You gave me 1,000. There is an n for which the natural log of n is 1,000. You gave me 10 trillion. There is a number for which the natural log of n is 10 trillion. That's one way you can show that it diverges, is that there is no example of a number that the natural log doesn't reach. Yeah.
So what you're saying is that if we interview n candidates, we'll only hire natural log of n.
Yeah, proportionally to the natural log of n candidates. Yep, that is how we would read that. And we use an indicator random variable. And one interesting point that it makes sense that if you've interviewed I candidates, the probability that candidate I is the best candidate is 1/i.
Yeah, and so how's translating into ln and well anything? I'm sorry, I'm confused.
You're good, but so we just need to find this sum from 1 to n of 1/i. It's the first n terms of the harmonic series. And the harmonic series grows at the proportion of the natural log.
Oh, now.
So we can state that if we interviewed n candidates, according to this method, we would hire the natural log of them, which is an interesting result.
All right. Why the big O 1 constant at the end though? Kind of curious about that.
Yeah, so it just means that there may be some additional constants on the end of that to increase or decrease the amount. It's proportional to the natural log. It's not exactly equal to the natural log, but it grows at the rate of the natural log.
Well, what I asked.
Yeah, no, that's good. That's a great question.
I really gotta work on my terminology. All right.
So here's a conclusion to the hiring problem. At least this base hiring problem. We'll come back to this in a bit with an additional question about it. But we're going to answer a couple of other questions first. The first one we're going to tackle, if you've heard of it before, is the birthday paradox.
Oh yay.
Have people heard of the birthday paradox?
Yes. Is it the one where if you get 20 people in a room, there's a
high likelihood that they may ship that they'll share. the
Yeah.
birthday?
So
Oh, yeah.
the birthday paradox is basically exactly that. How many people must be in a room before there is a 50% chance that some two people in the room share a birthday? So I want people to write an estimate on a piece of paper and store it for later, just to test your intuition. There are 365 days in the year, 366 if we're counting a leap day. So we should make a couple of assumptions. There are always 365 days in a year. We're not going to care about leap days. Sorry to anyone who has a leap day birthday. My cousin does. She doesn't exist to me. It's not a real birthday.
Wow.
She party once every 4 years.
She parties every day. You only get a birthday every 4 years. You feel like the world is out to you.
In your 20s and a birthday every couple of years.
So other assumptions we should make, birthdays are randomly distributed. This is not actually the case, but you can imagine that there is an equal chance given a random person that were born on an arbitrary day of the year. And birthdays are also independent. There's nothing that says that college-age students have a similar distribution of birthdays. So they're completely independent. Any two people for any reason are equally likely to have the same birthday.
In the past, I would have suggested a gigantic number, but I have a feeling it's not so simple.
So let's start with, we grab two random people. What is the probability that they share the same birthday?
1/360.
That's right.
Yeah.
Why is it 1/365? Yeah, you take the first person for granted, right? Their birthday doesn't matter. The question is, does the second person's birthday match whatever that birthday happens to be? If person one's birthday is January 1st, there's a 1 in 365 chance that the second person has a birthday that is also on January 1st. So the first person's birthday doesn't matter, the second person's birthday does matter, and that it has to match the first person's birthday. All right, similar but different question. Probability that two random people share a birthday that's on a specific chosen day. So I pick a day, November 18th. And then I say, you and you, random people. What is the chance that both of their birthdays fall on exactly November 18th?
Over 365.
Not the worst idea I've heard.
It's not correct, but it's a good idea.
Over 365 times.
Yeah, 1/365 squared. Yeah, that's exactly right.
Oh, yeah.
So both of the people, now the chance, the first person has exactly that birthday is 1 in 365. Independently, that second person has a 1 in 365 chance to have that exact birthday. So the chance they both do, you multiply. So this becomes a little bit easier, rephrasing the question and think about it as the probability that at least two birthdays match is 1 minus the probability that all birthdays are different. Does that make sense? Really, that becomes a binary problem. Are everybody's birthdays distinct or not? If we have not, then there are at least two people who share the same birthday, which answers the question. So it becomes easier, rather than asking what is the chance that two people, and looking at all possible pairs of people and all possible days of the year, we're going to look at the probability that their birthdays are all distinct. And if we find that probability, we just have to subtract it from 1 to get the answer of at least two people sharing the same birthday. We agree on that? Does that make intuitive sense? Okay, let's define this recursively. We have a room full of k minus 1 people. And then person k walks into the room. So we look at the probability that all k minus 1, everyone before the person walked into the room, shares or has a different birthday. Then if we had that answer, then the probability based on the k people when the k person walks in the room, we're going to ask the question, does the kth person share a birthday with person 1, person 2, person 3, person 4, all the way to person k minus 1? And only if all of those are distinct can we add person k to the room of distinct birthdays. Does that make sense? So with a room full of 0 people, k is 1, the first person enters the room. There is no one to compare them to, they're in the room. Person 2 walks in the room. You have to compare person 2 to person 1. That goes back to 2 people sharing the same birthday. So there's a 1 in 365 chance, once the second person comes into the room, that these 2 people share the same birthday. 364 out of 365 times, their birthdays are distinct. Then we add a third person. And to add that third person to the room of distinct birthdays, we have to compare them to person 1 and say, is your birthday distinct from person 1? Is your birthday distinct from person 2? If both of those are true, we can add person 3 to the room as having distinct birthdays. So I'm describing kind of the base case and building on the base case. Probability that a room with 1 person has every person with a distinct birthday, that probability is 1. There's no way for 2 people to have the same birthday if there's only 1 person in the room. So that's your base case. As we expand, we start to see how this evolves mathematically based on this intuitive idea. So the probability that all birthdays are distinct with k minus 1 people in the room breaks down recursively into the probability that the probability that all k have distinct birthdays. Probability that all k minus 1 have distinct birthdays times the probability that the kth person, given that the k minus 1 people are distinct, the probability that they have a distinct birthday from all of those people breaks down into that. And we can see that as this expands, we end up with a solution. We can simplify from here. So we know that a rule we can apply is 1 plus x is less than or equal to e to the x for all x. So that allows us to apply here and basically determine that the probability that the kth person having a distinct birthday boils down to less than or equal to 1/2. So probability that all k birthdays are distinct and at most 1/2 when k times k minus 1 is greater than or equal to 2 times n log 2. That's the natural log. You're not expected to be able to analyze this to this level, but again, this is how you would go about solving this problem and getting an answer. Because we want to query what is the probability that we're trying to answer the question, when is it 50% likely that 2 people share a birthday? So we need this to be less than or equal to 1/2. We're solving this for less than or equal to 1/2. Where is that 1/2 point when we reach 50%? Who thinks they have the best guess? Anyone willing to guess that they have the best guess in the class with regards to that?
I'm putting down,
Confidence, I like it.
I'm putting down number 35.
35? 35 people in the room. There's a 50% chance the 2 of them share the same birthday. How many people wrote down something bigger than 35? How many people wrote down something less than 35?
Honestly, yeah, I wasn't entirely sure my stuff, let's be honest.
Yeah, it's a bit of an interesting result. The answer
What?
23. How can we intuitively make that make sense? Yeah,
You do like 1/365 for 2 people and then add it to 3 people.
yeah, in order to do that, there's one assumption that we are making, which is that the K -1 people are all distinct. So we have to figure out the probability that when we add a second person, we add a third person, we only continue until we're 50% likely that we're going to say yes or no. Where is that 50% likely place to stop? And the answer is at 23 people. But if there are 22 people in the room and we add a 23rd person, it's about a 50-50 between whether we terminate there or whether we keep going.
Wow. I was actually close. I actually wrote down 25.
Dang, should have raised your hand.
Good,
Dang.
he beat me to it.
I'm
Don't-
not-
Don't worry, no offense, none.
So now I'm going to phrase a secondary problem to this, which is that the number of days on Mars in a year is 669. How many Martians would we have to add to the room before we are 50% likely that 2 Martians share the same birthday? Instead of 365 days in the year, there are 669 birthdays in the year. Not quite double, but anyone want to take a guess as to how many Martians we'd have to have in a room before we are 50% likely for 2 Martians to share the same birthday?
Yeah, count that all Martians are triplets.
Probably, I'm going to say 39.
They're independent. There is no such thing as
I'm still gonna bet it all on lucky number 35.
42.
35, 42. Any other guesses?
I put 39 already.
39? You're all overestimating.
Really?
31.
I am not going on the roulette table.
So if you're curious again about kind of the why, it's tough to break this down into exactly the why within the periods of class that we have for lecture, but I find this to be a very interesting section to just go read, think about, try to make sense of, draw out some work, try to make this make sense. And math reveals its underlying intricacies as you spend more time just trying to figure out, when you find an interesting result like this, why is it the case? I find that most people find these results unintuitive. You overestimate how many people have to be in a room. So, I don't know, are there 23 people in this room?
8,
5, 10,
8,
14, 18. We do. We have more than 22 people in this, 23 people in this room, just barely.
Oh.
So there is more than a 50% chance that 2 of you share the same birthday.
Shout out.
It's something that we can try to figure out if we care. Yeah.
Yeah, to answer the question for me, that whether the result is intuitive, I can understand the 1 in 365 for 2 people in the room.
Yeah.
And I can understand that there is a 100% chance if there are 366 people in the room.
Mm-hmm.
And so that's where I'm kind of stuck. It's like, okay, well, this exists somewhere in between those two, like, axioms.
Yeah, it has to be, for sure. But why is it not half? Why is it not half the people? It's because you're comparing each new person to every existing person. And each one of those independent variables has a 1 in 365 chance of being true. So when you bring in the 8th person, you're not looking at 1 new birthday. You're looking at 8 pairs of birthdays, each of which have a 1 in 365. And when you bring in a new person, you're looking at 1 more set of pairings. And that set of pairings grows, each with likelihood 1 in 365. So it scales more quadratically than linearly as you introduce more and more new people. It's very interesting. Oh no, I failed to animate this slide quite correctly. I missed something. Oh well, my mistake. I get to make fun of myself. What is that? We'll get there. Next problem we're gonna look at with just not too long to at least get started on this is called balls and bins. This is also taken out of the book, but I picked the ones that I found to be the most intriguing out of the book, the ones to come and describe in class. So let's test our intuition once again, because I like doing this. We are usually pretty intuitive people, but it comes with some mathematical backing. We can be more intuitive to try to understand why what seems unintuitive to us and make that more intuitive so that you can go make fun of your friends.
Interesting.
So we have some number of bins in front of us, and we're going to toss balls into those bins. When we make a toss, each ball is equally likely to end up in each bin. So we have N balls and B bins. So there are some interesting questions we might choose to ask about this situation or this setting. At the end of the process, how many balls do we expect to be in the first bin? Given that there were N balls and B bins. So your answer should relate to both N and B. N over B would be the expectation. What makes you say that?
You think they'd be equally distributed, isn't it?
Yeah, we can use an indicator random variable. When you throw the first ball, what is the chance that it ends up in the first bin? 1 over B. When you throw the second ball, what is the chance that it ends up in the first bin? N over B. Or sorry, 1 over B. So the sum total when you throw N balls would be N over B, the expectation, since these are again independent events. It doesn't matter where the first ball ended up when you throw the second ball. That doesn't change the probability that it ends up in the first bin. So yeah, ends up as a binomial distribution, N trials, 1 over B probability of success, and that gets us N over B. Next question. We're going to get harder and harder with each question. How many balls must we toss on average before the first bin contains a ball? How would we figure that one out?
I feel like something like N minus B divided by B bins or something. Because if they're equally likely to be distributed, then whatever N balls you could throw into B bins. No, I didn't think that. Yeah, but it well at least one. We don't know what B bins are in a way, but I need to work on understanding my reasoning still. But I think I understand. I think I have a good idea.
Yeah.
Is it B times?
It is exactly B times. What makes you say that?
Because we want the probability when we're looking at that to be 1.
Mm-hmm.
So in order for that to be 1, N must be equal to P, that must be equal to.
Yeah, it ends up being a geometric distribution. The probability that the first one ends up is 1 over B. We only continue this process if we failed at the first ball. So the probability of the exact second ball being the first one that goes in the first bin is the probability that the first ball didn't go in the first bin, which is B minus 1 over B. And then the probability that that one goes in is 1 over B. For the third ball to be the first one that goes in the first bin, we need the first ball and the second ball to have not gone in the first bin, and the third ball to go in the first bin. We take that geometric distribution and find the sum, and it is exactly B. The parameter of the geometric distribution is 1 over B, probability of success. And intuitively, on average, it will take us B attempts. But the underlying reasoning turns out to be a geometric distribution. How many balls must be tossed on average before every bin contains at least 1 ball?
Every bin, eh? B squared would be what I'm thinking, but it's not,
Not a terrible guess.
no, but. Still, it is missing something, let's see.
Yeah, it can't be B because that's the probability that the first bin gets the first ball. We need every bin to get it. So that would only be the case if the first bin was the last bin to get a ball.
Yeah, but it's not
That's
always
not guaranteed.
guaranteed the case.
Right. So there's gonna be more to it than that. It's gonna take more trials on average to get every bin a ball than it did just the first bin.
Or. Well, let's see, each one is what very likely, and we're doing with B and we. Tossing it like. Then we're tossing like end balls and trying to hit all bins. Thinking of. What's the thing?
Yeah.
Yeah, I'm kind of in the same spot as him. Every time
Yeah.
we toss ball, that we can subtract a bin.
Potentially, if it's the first one, if it's the first chance, first time that bin has had a ball in it. So on the very first toss, we're guaranteed that it enters a new bin. On the second toss, what is the chance that that second toss eliminates another bin? It's the first bin that it's in. B minus 1 over B. The only time it's not eliminating a new one is if it hits the exact same bin the first ball did.
Makes sense.
We can carry that logic on for, now we have a branching factor of 2 though. We have to determine what is the probability that the second ball was in a different bin from the first, and the second ball was in a first bin from the first. So we could create a very large tree from this. And branch that out. That turns out to be unnecessarily complicated. So we can use induction for this.
Yeah,
So if B equals 1, how many tosses are required? We know that the first ball has to go in the only bin. It's going to be 1. There's going to be 1 trial to get there. So when B equals 1, the answer is 1. When B equals 2, the first ball will go in an empty bin. The second ball has a 1 in 2 chance to go into an empty bin
yeah,
and end the episode. But in the 1 in 2 chance it doesn't, we need to repeat that process until it's basically the same thing as flipping a coin until we get heads or tails, doesn't matter which. But we're going to repeat a 50% chance until we get a success. The next ball goes in the empty bin. You can extend that to 3 bins. And try to come up with an expression. The sum from I equals 1 to B of the chance that we're hitting a new bin with that ball. So, yeah. N is the total tosses, N sub I, number of tosses needed to get from I minus 1 bins with at least 1 ball to I bins with at least 1 ball. What is the expected value of that? I'll leave this as the dangling question because we are out of time. I'll let you think about that over the weekend. But we'll come back in an answer to that and come back to the high rate problem as basically I want to motivate a bunch of different kinds of examples where probabilistic analysis is useful if you were going to write a program that simulated something like this. I have office hours starting now, and I can guarantee that I will be in there until my afternoon lab at 1. So I have 3 hours of office hours. Let me know how I can be useful.
wow, okay.
Party in my office, BYOB, bring your own brain.